Today we have Professor Arno Puder from San Francisco State University. Professor Puder, prior to his current position at SFSU, he worked for AT&T Labs Research and German Telekom. His research interests include middleware, ubiquitous computing, and applications for sensor networks. Today he is going to talk about cross-compiling Android applications to the iPhone. And I'll give it to Professor Puder then.
Okay, thank you, Lei, for the introduction, and well, thank you for inviting me to talk about my research. Smartphones have become very popular, and in particular, those two that I've mentioned on my slide here on the title slide, Android and iPhone, have certainly created quite some buzz. And as more and more of these smartphones are released, of course, the problem also increases in terms of deploying your application on different smartphones. So the technology I'm going to talk about today is helping you porting applications from one smartphone to another. And in particular, I will be talking today about, well, as the title suggests, cross-compiling Android applications to the iPhone. Now, before I go into any technical details, I wanted to just briefly introduce the team. Now, of course, with any open source project, and XMLVM is an open source project, you stand on the shoulder of giants. So XMLVM as an open source project is making use of over half a dozen other open source projects, but it always boils down to the people. So within our project, there are a number of people who have made significant contributions to XMLVM. So the core team, besides myself, is Sascha Heberling, who is actually another Googler. He works out of the Zurich office, and Wolfgang Korn, who works for a consulting company in Germany, Blukarat. And Blukarat is also a corporate sponsor of our project. Now, as a growing open source project, we also have now a growing number of people who make contributions to XMLVM. And at least as of today, I list those names that of people who have done some work in our project. Well, a bit of background. I guess it goes without saying that smartphones certainly are getting very, very interesting. If you look at the growth rates, so they have double-digit growth rates, and that, I'm sure, is going to persist for quite some time to come. Now, if you're an application developer, then you are faced with the problem of rewriting your application for the various platforms, and that can consume a lot of time and resources. Now, while the programming environment is a little bit different, the smartphones do have similar capabilities when it comes to their hardware features. So again, the problem here is that you as a developer are faced with this problem of deploying your application cross-platform. And on the next slide here, I've put down some, well, kind of a little snapshot here. So on the first column, I have the HTC G1. I have on the second column the iPhone 3GS, and the third column, I have the Palm Pre. Now, Android is releasing more and more devices, and Google has just recently released its Nexus 1. So of course, even with an Android, there is now a multitude of different devices out there. But again, like for the slide here, I guess the important point is if you look at the upper part of that slide, I give you a little background on the hardware details on the various devices. And you can see they're almost, well, at least very similar. And if I keep on adding more devices here, they probably will be the same in terms of speed, in terms of CPU, in terms of RAM. But then if you look on the bottom half of this slide, you will see that they're actually quite different when it comes to how we have to develop an application for them. So I mean, you as a developer, of course, you look at the smartphone from an SDK perspective. So how do you actually write an application for the phone? And if you look at Android, well, Android is using Java as the language to write an Android application. And the GUI is based on well, a specific Android API that you make use of writing an Android application. You have virtual machine technology is allowed on that phone, and everything is open source. Well, I mean, it's a little bit of a caveat, of course, that there are some proprietary parts that Google does not turn into open source, but at least for the base SDK, everything is open source. Now, if you look at the iPhone, that's completely radically different. So you have a language called Objective-C. And I will say a few more things about Objective-C on the following slides. Furthermore, you have a proprietary API called Coco Touch for writing iPhone applications. And of course, the complete tool chain is proprietary. Actually, you need even a Mac platform in order to write an iPhone application. Now, I also want to say a few things about the Palm Pre. Actually, it's a device I like very much. I think it's unfortunately a little bit underrated. It should be given a bit more attention if you ask me. But if you look at how to write Palm Pre applications, they actually have decided to make use of web technology. So if you want to write a native Palm Pre application, you end up writing HTML, CSS, and JavaScript, almost as if you are writing a web application. So again, like the point of that slide is here that while the phones are somewhat similar on the hardware side, they are radically different from the way you actually write applications for these phones. So the proposed solution that I'm going to go into some detail here in this presentation is that we say, well, as kind of a frame of reference, we take Android. So we expect people to use Android, and we do that for various reasons. Well, first of all, I mean, I'm in the education business, and there's certainly a lot more skill set out there for Java than there is, for example, for Objective-C. So if you look at how much innovation you can achieve, certainly I would argue that basing on Java is certainly a smarter choice than Objective-C. So I'm not looking at the current number of applications you have currently in the App Store. I'm looking overall at the skill set that you have out in the industry. The second thing is that Android was built from day one, or was designed from day one, to serve a heterogeneous set of devices. So in particular, Android copes very well with different screen resolutions. And the iPhone, for example, is only doing that now. Apple has recently announced the iPad, and only now Apple is faced with that problem of having two different devices, the iPhone and the iPad, that have different screen resolutions. So only now, actually, they're beefing up enhancing their SDK to also support different screen resolutions. So from that perspective, it makes a lot of sense to take Android as the frame of reference. And then what we do in our tool chain, that kind of is also the outline for the rest of this presentation. So the first step that we do is, or that we did rather, is to design a Java API for Coco Touch. Remember that Coco Touch is based on Objective-C, so the first step will be to create a Java abstraction on Coco Touch. The next step is going to be to cross-compile Java to Objective-C. Since we're starting from Android, then we want to go over to Objective-C, we have to cross-compile that somehow. And maybe I should also stress this point, because the iPhone, or Apple rather, prohibits by license agreement the use of virtual machine technology on the iPhone. So you cannot run a virtual machine on the iPhone. But by cross-compiling, we actually end up with a native application that does not require a virtual machine. So our tool set is within the legal framework of the Apple SDK. Now, the last step that we have to do is to deal with the API mapping. So if you write an Android application that has a different kind of API than the iPhone, obviously. And the last step that I will be talking about today is how we deal with that through what we call the Android Compatibility Library. So as a programmer, as a geek, the first thing you do in any programming language is Hello World. So what does Hello World look like for the iPhone? Well, as I mentioned before, the iPhone is based on Objective-C. So if you want to write a native application for the iPhone, you have to do that in Objective-C. Now, I tell my students sometimes that Objective-C is like the language Latin. You know, there's exactly one country in this world where Latin is being spoken, that is the Vatican, of course. So Objective-C is used inside of Apple, but not used much outside of Apple. And it is a dynamically typed language. It's a strict superset of the C programming language. So every legal C program is also a legal Objective-C program. And what you see here is, again, is the Hello World program. And if you've done any kind of GUI programming, then probably you will make sense of it rather quickly. One thing you often notice, or the first thing you often notice when you look at your first Objective-C program, is that you see all these square brackets. And these square brackets denote method invocations. So whenever you see a square bracket, the first argument is actually then the target, which can either be a class object or an instance. And then you have a list of named parameters that you're sending to that object. So for example, if you look at the first thing here, UI screen, main screen, basically UI screen is a class of the Cocoa framework, Cocoa Touch framework, and you ask it to give back the main screen. So what you get back is a pointer to this object. And you can actually see here C shimmering through a little bit because you still have these pointers that you have to deal with in Objective-C. Now, if you look at the rest of this program, I think you can probably make sense rather quickly if you done, for example, some swing programming. So if you look at class UI window that is being used here a little bit down, that kind of corresponds to a JFrame if you have ever done any swing programming. UI view you might correspond, or you might take an analogy to a JPanel. UI label then again corresponds to something like a JLabel in Swing. So with that, I think you can probably understand what is happening here. Just maybe a few side notes here. First of all, the entry point of an iPhone application is a method that you have to overload that is called application did finish launching. So that is, I didn't come up with that name, that is the official API as defined by the iPhone SDK. So that is going to be the first thing that is going to be called of your iPhone application. Of course, you have to derive your application class from base class UI application in order to override this method. But that will basically then kick off your program. That's the first thing I want to point out. The second thing I want to point out, I already mentioned that Objective-C is a superset of C. So that's why you have these pointers. I want to point out the second line here of my implementation, and I'm not sure if you can see the mouse here. So basically, I ask the screen object for its resolution, and I get back something of type CGRect. Now, you will notice that there is no pointer here. Actually, CGRect is a simple struct. And unlike C++, a struct is not a class. A struct is just simply a value type. So what is happening here, actually, you are being given back a struct that is copied by a deep copy mechanism here. I want to point that out because Java, as you know, does not have value types. So when we do API mapping, we have to also kind of bridge this, well, you might call it a problem. When we have value types in Objective-C, we have to represent it somehow on the Java side. So this here is now the Objective-C version of Hello World for the iPhone. So the first thing that we have done in our framework is to come up with a Java API. So on this slide now, what you see is a Java program that is basically using our API mapping for Cocoa Touch, but it's, well, first of all, 100% Java, but it has the same semantics. So with all I've said on the previous slide, I guess you can immediately understand what is happening here. So we've kept the naming convention, so you see you have to derive your application class from base class called UI application. You have to override a method called application did finish launching, and then also the other classes, UI screen, UI window, we just have taken the same names, of course, as we have found them on the Objective-C side. So we are trying to mimic the API from Cocoa Touch that we see on the Objective-C side as closely as possible on the Java side to make it more easier for a programmer to make that transition. So ideally, you can even go to the Cocoa Touch API documentation and then kind of understand what these classes are doing. But of course, we have taken some design decisions here in terms of staying closer to the nature of Java. So we have made use of strongly typed interfaces for one thing. So wherever we see something dynamically typed on the Objective-C side, we're making use of Java interfaces. And also, like, for example, here constructors. We are using constructors a little bit more the way they are supposed to in Java. It's also a little bit different the way it's done in Objective-C. So if you take a look at this slide here now, so if you take this Java source code here, then basically what happens in our tool chain is that we cross-compile this Java source code over to Objective-C source code. And how we do that, I will explain on the next few slides. But once we have it cross-compiled to Objective-C source code, we link it against a little library that we call here Objective-C wrapper classes. And then what we end up with is a native executable on the iPhone. So there's no need for a virtual machine. So you can deploy that on your iPhone. And again, since we're within the legal frameworks of the Apple SDK, we can also push it on the App Store, of course. Now, if you remember, even the little Hello World application I had on the previous slide was making use of a class called UI screen, UI window, UI label. Now what you can do is, and that is what I have now on the slide here, what you can do is you can actually provide a Java-only implementation of these classes. So if you have a class like UI window, instead of just having a skeleton, why not just implement it also based, for example, on Java 2D? What you end up with is a 100% pure Java version of your iPhone application that you can run on any platform. So any platform that supports Java, you can now run, basically it's our own Java-based iPhone emulator that allows you to run your Java-based iPhone applications. And I want to switch over for the first demo to explain how this works. And I'm in Eclipse here, and I'm going to launch now a little application that is kind of our trademark application called Fireworks. And it does not a whole lot. It just switches into full screen mode, and then it does a little fireworks. And I have my iPod Touch here, so if I call Fireworks here on this device, then of course you see the same thing. Now, there's one little gimmick to this application. When we turn it around, we use the accelerometer, so you will notice on the device here, if you can see that the sparks always follow gravity. So no matter how I turn the device, the stars will always go to the bottom. So, and we have mimicked this behavior in our own Java emulator here by these scroll bars. So if I modify these scroll bars here by feeding different values into the accelerometer, then you can see that the stars start flying into different directions. Now again, I want to stress what the application you see here, that the thing is that what is called iPhone Simulator is a 100% pure Java application. You can run that under Windows, under Linux, and the application that you have seen on my iPod Touch is just the cross-compiled version of the application. Of course, on the device, the classes are linked against the Cocoa Touch classes, so to yield the behavior that you have seen. There's a little bit more that's kind of a fun thing. So here actually I have on my iPod Touch a little remote control application. And what I can do is I've created an ad hoc network between my iPod Touch and my laptop here. So what I'm going to do now is I'm going to punch in the IP address of my laptop. I hope I get this right here. So what happens now is my iPod Touch acts as a remote control for my Java-based emulator. And what happens is when I turn my iPod Touch, you will see that, well, you can see that the scroll bars kind of turn by magic. So basically, the readings from my iPod Touch are being sent via an HTTP request to our Java-based emulator. So when I turn the device, my iPod Touch, it kind of, if I turn it upside down, my device and the stars in my Java emulator start flying up. Now this application that I've used here on my iPod Touch, we've actually implemented using our own technology. So what I can do now is I can go back to Eclipse and I can just simply run a second instance of our Java emulator. And what you see now here is actually the interface I've just seen on my iPod Touch. So I still have the Fireworks running here in parallel, but what I can do now is, since I'm running both emulators on the same laptop, I can just simply type in the loopback IP address. I can turn this on, and if I now use the controls on the one emulator, you can see that it reacts over on the second emulator. So if, for example, I go up here with X, it starts going left and right. So you can see that actually for our Java-based emulator, we have already pushed it to some extent here. So all that you see here, again, on the second emulator is just a Java implementation. So we have mimicked a little bit the look and feel of the iPhone by providing a Java 2D implementation of the Cocoa GUI elements. So let me go back to my presentation. And so let me talk about some of the challenges that we're facing. Before I actually tell you how we do certain things, let me tell you first about the problems that you have in trying to do so. Well, first of all, as I mentioned before, as a design goal, we try to mimic the Java API as closely one-to-one as we see from the Objective-C API. but we make use of strongly typed interfaces. So just to stay in the spirit of the Java programming language. Now, when it comes to challenges, there are challenges related to the language cross-compilation. There are challenges related to the API. And let me first talk about the Objective-C challenges. Well, first of all, Objective-C has no namespaces. Objective-C does not permit method overloading. So they allow method overriding, but not method overloading. So Java supports both. So when you cross-compile, you have to deal with that somehow. The version of Objective-C that's being used on the iPhone does not have a garbage collector. So if you write an iPhone application, you actually have to make use of a reference counting mechanism that is given to you by the iPhone framework, but it's your responsibility as a developer to actually correctly retain and release object references. So since we don't have a garbage collector on the iPhone, what we do is actually during our cross-compilation, we insert these retain and releases during the cross-compilation phase. Now, of course, if you're familiar with garbage collection, you will know that if you do reference counting, although it's more efficient than garbage collection, but it does have some limitations. So, for example, if you have a cyclic data structure, that cannot be reclaimed by reference counting. So that is one of the limitations that we have right now in our tool chain. So if you have a cycle in your data structures that you build up, then you need to break that cycle manually by assigning a null pointer somewhere. Once you do that, of course, then we can reclaim memory. But if you just have a cycle in your data structures, at this point, we cannot garbage collect that. Now, the challenges we have on the API level, well, there are quite a few. Well, first of all, the Cocoa API is not as cleanly designed as you might think. So for one thing, it's not always object orientation that they have used in designing the API. So you actually will see quite a few C functions there for doing certain things. So for example, I've highlighted just one here, CGColorCreate creates a color object, but that actually is a C function. So you have to provide it the RGB values, and then what you get back is something that you can use as a color value. But this function here is actually a function in the C programming language sense. So it's not like a static method of a class as you would expect in a clean object-oriented design, but it's just a function. There's a question here.
Why is that particularly worse?
I wouldn't say it's worse. It's just I mean it comes from historic background. So of course the Quartz framework has been there for quite some time, and
does that introduce some sort of challenge to the cross-compilation?
Well, okay, the question is that creates some challenge in cross-compilation. Well, it does, because remember we cross-compile from Java to Objective-C. So whatever we see on the Objective-C side, we have to create some Java API for it. So since there are no functions in Java, we have to create some static method of some class. So we have to basically turn this more procedural interface into an object-oriented interface. So that's the challenge that we had to deal with. I'm not saying that what Apple has done is bad here. It's just legacy, basically. The other things that I already mentioned before, like value types. If you look at CGRect, that is actually not a class. It's just simply a value type. So there are no value types in Java. So I didn't point that out in that slide earlier, but you might remember that actually there was a Java class called CGRect. So again, value types you don't have something equivalent on the Java side. So here we again map it to a proper Java class. But during the API mapping, of course, we have to map a Java class to a value type on the Objective-C side. So that happens inside these wrapper classes. The next thing that kind of caused us some headaches is that, well, at least the design of the Cocoa API is using some old little tricks that people might remember, the older people in the audience at least, from the C programming language. So if you need additional output parameters, there's a common trick to have a pointer to a pointer, basically to pass back additional output arguments. Now, Java only supports call by value, so you cannot do call by reference. So again, from the Java API design perspective, we have to deal with that. And what we have done here is to create some holder classes that basically just act as a wrapper around an output argument. And the last part is, again, the delegation that is heavily being used in Cocoa Touch. And as I mentioned before, here, generally, we have turned that into a strongly typed Java interface, also to stay truthful to the spirit of Java. So let me explain to you how we actually cross-compile Java to Objective-C. And the first thing is that we do not have a Java source code level cross-compiler. So what our toolchain, what XMLVM actually cross-compiles is not Java source code, but Java bytecode. And more specifically, we are making use of the Dalvik virtual machine, or the DEX instruction set. So you might know that Android is not making use of the standard JVM, but Android has chosen their own virtual machine called Dalvik. And the bytecode instructions are called DEX, or DEX instruction set. The big advantage of DEX is that it's a register-based instruction set. So the Java virtual machine is based on a stack machine, but Dalvik is based on a register machine. So we're making use of that, and the first thing that we do in our tool chain is to take the Java source code and turn that into an XML file where the implementation is represented by the Dalvik instruction set. So to show you how this works, on this slide here, you see a very simple Java class. So you see a class called Calc. It has one static member, one static method called add. It just takes two integers, and all it does is just simply return the sum. So it returns x plus y. So in our toolchain, what happens is, well, first you just take a standard Java compiler to turn it into a class file. And then by piping it through our toolchain, and again, by making use of the open source tool that we have access to from Android, we turn that into an XML file that just simply represents the Dalvik instruction set, but marked up through XML. So what you see on the next slide is basically this class Calc, but now marked up as XML and making use of the Dalvik instruction set. So it looks a little bit complicated, but if you take a closer look, it's actually not that difficult to understand. On the top level, you have a tag called class, that is your class definition. Then you have a method that is the add method we had before. You have attributes to denote the various properties, the modifiers that you have for this method, like in this case it's a static method. You have a signature, so you can clearly see that this method takes two integers as input. It takes it returns one int as a result. And then most importantly, down here, you see that in the code tag code, you actually have the DEX instructions that make up the implementation of method add by means of Dalvik instructions. And you see actually there are only two instructions here. There is an add int instruction and there is a return instruction. Now the add int instruction makes reference to three registers, Vx, Vy, Vz. And what happens inside the Dalvik virtual machine, that the certain registers are being initialized with the input argument. So actually by convention, and I won't go into too many details here, but register number 1 and register number 2 correspond with the input arguments x and y. So basically what this one instruction add int does here, it will add the content of register 1 with register 2, and it will store the sum in register 0. That's exactly what my Java class was doing that I had on the previous slide. And the second Dalvik instruction here then says return, and we're returning the content of register 0 as the result of this method. So that's kind of like a little inside glimpse into what actually happens inside of Dalvik that runs on any Android phone. So, but why do we convert this to XML? Well, that's also where the project XMLVM gets its name from, because we're using XML technologies for then generating high-level languages. So in particular, what we do now is we're using XSL style sheets for the code generation. So on the next slide, I give you one example on how we map this add in instruction to source code again. And what you see on the bottom here is now an XSL template that will always fire, it will always match whenever it comes across the add in instruction that I explained on the previous slide. But then what happens is that whenever the XSL processor is coming across that add-in instruction, it is going to emit this code that I have here in the as children of this template. And basically the code that will be generated is what I have here in this little yellow box here. So basically this one add-in instruction is going to result in this here, r1.i plus r2.i, and that is being assigned to r0.i. Now these registers here, r0, r1, r2, are based on a union that is of type XMLVM LM. So because a register in Dalvik can hold different data types. It can hold an integer, it can hold a float, for example. So, and this union here represents all these different possible types that can be stored in a register. And since we have the instruction add in, we know that what is in those registers are integers. That's why we are accessing the value through the .i discriminator. But you can see in terms of code generation, so for each Dalvik instruction, we have like a very small, very easy to understand template that will then basically generate code in the target language. Now on the next slide here, I'll show you the results. So if you take all our templates and if you run it through the XML file, I had 2 slides earlier, then here's the Objective-C source code that you would end up with. And again, you see, of course, the other templates that define all these registers here. So we have 3 registers. They're all of type XMLVM LM, as I explained before. You can see here the add method. And here you can see we're actually using name mangling to cope with this problem that Objective-C does not allow overloading. So we have our 2 input arguments, x and y, which here again on bytecode level are referred to as n1 and n2. We initialize the input parameters with the registers. Here's the one line, so the addition, that is basically the code that was contributed by the XSL template I showed on the previous slide. And then the return statement then will return the result. Now, of course, if you run this through GCC here, then there will some more optimization will be happening here. You will no longer see this actual assignment here, so you will do the add immediately on those N1 and 2. So actually, by cross-compiling DEX instructions, we are capable of generating fairly efficient code on the target language. Now we have different set of style sheets that do the very same for JavaScript. I mentioned earlier that we also support the Palm Pre. So we also have style sheets that just simply take this XML file that contains DEX instructions but maps then the DEX instruction set to JavaScript. So so we can actually then also cross-compile an Android application over to the iPhone. Sorry, to the Palm Pre. So up to this point, all I've talked about was the iPhone. I have not said anything about Android, right? So I come now to the next part of my presentation, because now that we have added a Java layer over the iPhone, basically the next step will be to take care of the API mapping from Android over to the iPhone. And if you look at it, the way you write an Android application, of course, you first of all use a Java language and you use an Android-specific API. So if you look on the far left of the slide, you can see the Android application that runs on top of Android is only making use of Android API. So whatever you see published as part of the Android SDK, that is what the application uses. Now what we do now is for the iPhone, so we have now what we call the Android Compatibility Library. That is built upon a common device layer. So basically within our compatibility library, we have a little abstraction that actually captures the essence of the smartphone, of the particularities of the smartphone, and those portions of Android that actually are generic to all smartphones. And I'll give you some examples on the next few slides. But the way this works is now that the Android Compatibility Library, it's also written in Java, of course, and it offers exactly the same API as the Android API gives you. And all of that is cross-compiled to Objective-C, so what you end up with is, again, a native application on the iPhone. Now we do the same thing over for the Palm Pre. So now, except, of course, here we cross-compile from Java to JavaScript. And we have a different WebOS layer that kind of adapts the common layer API to the way things are handled on the Palm Pre. So to give you some examples on how this looks like, let me give you 3 different examples. So first example. And the first example, I want to show you how we map an Android button over to an iPhone button. That's a fairly simple example. So if you look at an Android button, there's a class called button. It lives in namespace android.widget. And in our implementation of our XMLVM framework, what we do is we just basically, our implementation of the Android button is basically nothing more than a wrapper around a UI button. And this UI button that you see here in the first line of this class button is, of course, now the Java wrapper that we have created for the Cocoa Touch UI button. So UI button is the name of the class of the iPhone button. And I have one little example here. It's a little bit more sophisticated. If you have a button, of course, you want to install a click listener. Well, it's called a click listener in Android. So a click listener basically allows you to install a callback. Whenever the user presses the button, then the application will be notified via this callback. And there's a method called setOnClickListener, and you pass it an interface reference called onClickListener. And what we do in our implementation, now of course the UI button has something equivalent. There's actually a method called addTarget, and that serves conceptually the same purpose as the setOnClickListener on the Android side. Now, of course, there's a different way of defining this delegate, and on the Cocoa Touch side, there's something called UI control delegate. So basically, what we do here is we instantiate an anonymous class, we overwrite the raise event, and then inside the implementation of raise event, we basically send the click event back on the Android side. So what happens is, if your Android application is using an Android button, if you cross-compile it over to the iPhone, what you have on your native iPhone application is actually the UI button as given to you by the Cocoa Touch library. If you push that UI button on the iPhone, what will happen is it will call a raise event of that UI button. That raise event is then forwarding that to the reference the listener on click, which basically is the callback into your Android application. So that when you push the iPhone button, what will happen is here now that you will actually end up calling the callback inside your Android application. Now remember, all of that is being cross-compiled over to Objective-C. So also this little piece of code here will be cross-compiled over to Objective-C. Okay, second example. In Android, there's this infamous R class, and the way you reference resources in Android is via this R class. So if you have, for example, an external image, if you have a PNG file, the way you reference it is by making use of this R class. Now, Android will automatically create this R class for you. So what I have on the top here is what you will see is a little bit of that generated code that Android generates for you. So imagine if you have an image resource, a file called ball.png. Then what Android is going to do, it is going to create a field of a static final class called drawable that itself is nested inside of a public final class called R, the R class I just mentioned. And it will assign it some kind of unique ID that ideally you will not see. But when in your Android application, when you actually reference that, the way you do that is, so if for example, if you have an image view and you want to actually load it with that ball.png, what you do in Android is basically you say set image resource, and then you just simply reference this field of this public static final class by saying r.drawable.ball, and you can see it's exactly here, r.drawable.ball. So far, so good. That's the way the Android people have decided to design the API to reference external resources. Now, how do we deal with that during cross-compilation? Because when you think about it, this method here, setImageResource, actually it takes an integer. So at runtime, in our compatibility library, what we will see is we will see this awkward hex number here. So how do we actually map this back now to a file called ball.png? Well, what we do is we make use of Java reflection. And on the bottom of this slide here, I'll show you a little bit of code snippet that also comes out of our Android compatibility library. And basically what happens here is that you can see that we, first of all, we're asking for a class object of this r.drawable. So this $sign here is just the internal way for Java to represent nested classes on bytecode level. So our $drawable is just the way you reference the nested drawable class on bytecode level. But first thing we do is we just retrieve the class object. Then we're using Java reflection to get back all the declared fields, which is just basically an array of field. And this API comes from J2SE. So that's nothing magic. That is just standard Java stuff. And then you can iterate over all the fields, and then we can retrieve the name and we can retrieve the integer that is associated. So in particular, if we do this little for loop here, eventually we will see for the ID, we will see this hex number here, and for field name, we will see ball as a string. And from that, we can use then the string to create a file name and then to actually load the image resource. So we resolve those resources at runtime by making use of Java reflection. Now, once again, this piece of code on the bottom here is also cross-compiled over to Objective-C. So this will give you a bit of an idea that our cross-compile is actually fairly powerful in the way that it can deal with this kind of Java reflection. Third example, Android has layout managers. So Android, I mentioned before that Android is actually very well equipped to deal with different types of devices. And one nice feature about Android is that they have a way to describe user interfaces by declarative definitions. So there are some XML files that basically describe a user interface. And on the bottom here, I've just listed one of those XML files. So that is basically the schema of that XML file on the bottom is defined by the Android team. And what you see here is linear layout is one of the many layout managers that you have in Android. And basically, it just defines a vertical arrangement of different interface elements. And what you can see is here, this linear layout is just, it has an edit text, it has a text view, it has a button, and then another linear layout that is simply a wrapper around a little logo. And here, the screenshot on the right, you can actually see what it would look like in the preview of Eclipse. Now, Android is open source. Android has an implementation, has Java code that takes this XML file and basically parses this XML file, and it will render this user interface. So what we have done now is, since we are an open source project, why not simply leverage on the open source? So actually, we take the original Android source code of the layout manager implementation, we also just simply cross-compile it over to Objective-C. So at runtime, on the iPhone, we also copy these layout files over to the iPhone. So what happens at runtime on the iPhone, that we read in this XML file, and based on this declarative description of user interface, we actually then start building up the UI. So here again, we make use of open source, and you can also get a sense of what is all contained in our Android compatibility library. So it's partially things we had to implement ourselves, like the parsing of the R class or the wrapper for the widgets like button. But we also leverage the Android source code in the sense of bits and pieces that are device independent. So if you download XMLVM, there is a little application that we have done. Now, we are tool developers, we are not game developers, so don't expect too much of that application. It's a little application called Sokoban. It's actually, the gaming idea is fairly old. You have to, it's a little strategy game where you have to push, well, in this case, apples to target areas, and so the little guy in the middle has to push these apples to the white outline target areas. And the way we have done this game is by implementing it in Android. So we implemented it in Java, and it's only making use of Android API. So the screenshot in the lower right is just simply a screenshot of that original native Android version that we have implemented for the Sokoban game. Now, when we cross-compile that to the iPhone, it looks then like on the screenshot on the lower left side. Now, I mentioned before that Android is actually very well equipped with dealing in different device capabilities. So actually, the way we have written this Sokoban game is that we actually look at what is the screen resolution on the device. Now, on the iPhone, at least so far, it only has a certain resolution of 480 times 320. But the Nexus 1, for example, on the Android side has a higher resolution. So actually, our implementation of Sokoban renders nicely even on high-resolution screens. So this application has been pushed out to the App Store, Apple App Store, and also the Android market. So if you have an Android phone, if you have a Nexus 1, or if you have an iPhone, you can actually go to your respective markets and you can look for Sokoban. You can actually download the application. Now, I should make one little disclaimer here, because this screenshot is not exactly accurate. And if you actually do download the application, you will notice that's a little bit different from the screenshot here. And the difference is this little guy here in the middle, the Android. You know, initially we thought it's kind of like a little inside gag, you know, like Android pushing apples, you know. But Apple didn't like that. So actually I had an app reviewer call me, and he said, well, thou shalt not have other gods besides me. Well, he didn't say that literally, but what he basically said is they don't allow any competing, they don't allow references to competing products. So we had to replace the Android logo with something else. So So now we have the version you can actually download now is now we're using the Linux Penguin instead, and I guess for Apple that is not really a threat, so they have accepted the tux as the guy. Okay, that's going to be the last analogy between Apple and the Vatican I'm going to make here. So to give you an example of a much more complicated and a much more elaborate application. So we have been working with an Australian company called Funky Mobile Games. And this company specializes on games from mobile platforms. And they have created a version of a game Strategio for Android. So basically, they have a fairly elaborate implementation of this game for Android. And they have used our tool, XMLVM, to cross-compile their implementation of Legion over to the iPhone. Now, this application is making use of quite a few Android features. So they have they're making heavy use of activity lifecycle. They have sound. They have animation, they have custom dialogues, they use a lot of declarative layouts for the UI, and they also use file I/O for the serialization of the game state. They also have a fairly sophisticated AI engine, so there's a three-time world champion of this game, Strategio, who implemented this AI engine. So what I want to do now is actually I want to do another demo, and I want to actually show you this game of Legions side by side in both the Android emulator and also then the cross-compiled version for the iPhone. So let me first. So what I'm launching here now is the Android version, and I can turn up the sound just for a second here. I don't know if the microphone picks it up, but actually they have put a lot of effort into this game. So they have hired a composer for the music. They have hired a design artist for the graphics. So let me just turn off the sound here. So let me now launch the iPhone version. And here I'm in Xcode, so actually here I have loaded the cross-compiled Objective-C source code, and I'm just launching the same application now in the iPhone emulator. Whoa, and it's a lot louder. And you can see that's already like, you know, we're mapping the sound API here. So let me just turn down or also turn it off here to show you that you can do the same thing. So the first little thing that I want to point out, if you actually look a side-by-side difference of the screenshot, on the Android version you have this exit button here, which we don't have on the iPhone version. Apple does not permit exiting of an application on the iPhone other than pushing on the home button. So actually we offer a way to the Android developer to find out if your application is running under Android or the iPhone. And depending on which platform you run, you can actually then do things differently. So the Android version is actually also adding this exit button, which you cannot do on, well, you could do it on the iPhone, but Apple would not pass that through their app review. So there's like a help screen here. So if you click on help, then you have like some little help text here. You can go back to the main menu. Let me just do that here on the iPhone. Go back. Let me start a new game. So here, I don't know the rules of this game. I know that you have to place these elements here. So you have to pick like little soldiers and have to place them on the game board. That's like the first step of setting up the board. But what you then can also do is there's a feature called autofill, where you can just simply pick a random setup. Here's a little toast that says that. You can go back, you can say start game, it scrolls down the game field, and now you can start the game, or you can play the game. Let me do the same thing here on the iPhone. So again, you know, I have like this hovering pieces with the zoom feature. I can place them manually if I want to. I can also pick the autofill feature. I can go back, I can say start game. Again, it scrolls down here. Now I can play it by making moves, and again I'm not I don't really know how to play this game, so I'll just do something here. I just got killed, I know that. And then the AI is thinking, it's doing its counter move, and let me make something similar here on this side. So let me also pick maybe this here. So it does animation, it scrolls over here. Again, I got killed. And then let me just surrender here because I really don't know how to play this game. So you want to surrender as a custom dialog? Yes. And then we lose. It will tell you, it will actually open up all the fields. You can actually uncover it and see what you were playing against. Let me do the same thing here on the iPhone. Surrender, yes. And then you see the same thing here. So basically, apart from this one little thing with the exit button, everything else is 100% pure Android, 100% pure Java, all cross-compiled to Objective-C, all mapped from Android API over to the iPhone. So going back to my presentation, of course, the question is then how far can you push this? So I already mentioned a few times now that Android certainly is very well equipped with dealing with device heterogeneity. But what kind of applications can you actually cross-compile? Well, games are certainly a good candidate because games are not bound by user interface guidelines. You know, like you have like your image buttons and you have these custom dialogues, and apart from this exit button, actually you can pretty much do whatever you want. Now, if you have an application that is more based on widgets, if you have a more business type application, then of course things get a little bit more difficult. And the reason is that, of course, every handset, every smartphone has their own proprietary set of widgets. So basically, if you ask me, so what do you do in that case? Well, if you look at the model view controller paradigm, so the way you should be designing your application, what we can always cross-compile is the model. And we probably can also cross-compile a fair amount of the controller. Now, the view, you might want to do a custom re-implementation based on the particular smartphone. I mean, the iPhone is known for its very fancy widgets, so there's no point in trying to mimic an Android GUI on the iPhone. So probably a reasonable approach would be to actually then re-implement the view portion of your application, but making use of the smartphone-specific widgets, in that case iPhone. Now, of course, as I mentioned before, we have a Java abstraction around the iPhone now, so which means that even though you may have to re-implement the view for the iPhone, but at least you can do so based in Java. And one thing we're currently exploring is actually to mix iPhone and Android. So if you do a custom implementation of a view for the iPhone, that basically you can use an iPhone widget but embed it into the Android framework. So you can take, for example, like a picker, UI picker of the iPhone, and you can make use of it using a linear layout from Android. So that should be quite possible, and that's where we kind of are going to as a next step. So here's a quick overview of the complete XMLVM toolchain, and there are lots of little boxes here. XMLVM as a research project began in the early 2000s, and we have many other use cases that we can do. Well, XMLVM, I already mentioned XMLVM as a name, is derived from the fact that we have an XML representation of bytecode, and we're making use of XML technologies for doing cross-compilation. So actually, we do have a front end for .NET. We have a front end for Ruby bytecode, and we also have backends for different languages. Now, all these different paths you can take through this tool chain are of different maturity. Now, obviously, the smartphone portion is what attracts attention now to XMLVM. So that is the one that we're putting a lot of effort in right now, and that is the most stable. So what I've shown you so far right now is basically this here. So we go from Java class files down to Objective-C. So that is what I've shown you so far. Then we can also go down to JavaScript for the Palm Pre. But we can also do different things. So we can do something like, for example, we can go from .NET, and we can also go down to JavaScript. So it would be possible, for example, to write a C# application and cross-compile it over to JavaScript. Or we can also map .NET bytecode to Java bytecode. Again, the various paths through this tool chain are of different maturity. So in some cases, like this one in particular, I just highlighted on this slide, is more like a proof of concept. But at least it's in the code repository, and I guess you get the idea of where the project gets its name from. Well, I come to my last slide, and basically, you know, what I've told you about in the past hour is, well, we first have added a Java layer on top of the iPhone, and then we have created our own Android compatibility library to be able to cross-compile Android applications over to the iPhone. And I guess the benefits go without saying. Well, first of all, we support the skill set of people. I mean, there are a lot of Java programmers out there, and you can tap into their skill set. Android has a big momentum, so obviously, you know, supporting Android developers, and the only API that you have to know is Android. So we deal with all the device-specific details like iPhone and Palm Pre. So overall, it reduces the development cost, and it reduces the time to market. Well, since there's quite a bit of interest and on XMLVM, at least the smartphone portion, we are in the process of building up commercial support for XMLVM. And well, what we plan to offer is a broad range of different services around mobile applications, because we have noticed that quite a few companies are in this kind of situation where they want to be present in this app space, but they realize that they, first of all, lacking the knowledge of the various platforms, but also they realize the amount of effort they have to put in on targeting different devices. So kind of to fill that niche, that is where we are in the process of building up commercial support. Well, that comes to the end of my presentation. I would like to thank you for your attention, and if you have any questions, then I'd be happy to answer them.
I got a question here on VC. What is the support for things like OpenGL and things like compasses and some of the other hardware that's in Android but hasn't been in the iPhones, at least until recently?
Okay, so OpenGL, you were asking about OpenGL. So OpenGL, we actually do map. There was one guy who mapped the OpenGL API, so that's taken care of. The Compass API we don't have yet. Now, I mentioned before that Android actually is targeting different kinds of devices. So actually Android allows you to explore the capabilities of a device. So if you write a good Android application, it should cope with that situation where your application runs on a device that may not have all the features that you need. How you react to it, that is up to you. You may say, well, sorry, but I really need a Compass, and you don't have one on your device, so I cannot run. But we can certainly cross-compile that over to the iPhone. There's another question?
The choice to use XSLT for the code generation. Can you talk a little bit about that? I mean, it's a cute idea, but is it more than that? I mean, how would that compare to like an ad hoc, just parsing the DEX code and
Well, so the question is a bit more details about the style sheets we use. Well, like I mentioned, the product XMLVM itself came from the fact that I was trying to find ways of doing bytecode manipulations through XML technology. So earlier I talked about .NET. So actually we do data flow analysis using style sheets. It's maybe pushing a little bit too hard on the style sheet side, but I guess what attracts me for style sheets is just the declarative way of expressing code generation. So basically, the little template I've shown you earlier for describing the add-int, it's like a very clean and very nice, easy way to express what should happen when you come across an add-in instruction in your bytecode. Now, of course, you can implement it in different ways, right? I mean, there is no question that you can also just implement it in Java, for example, and that will no doubt be more efficient than if you do it in style sheets. But remember, the style sheet, running the style sheet happens at compile time, not at runtime. Yeah. So the inefficiency that we might have in slightly longer compilation times refers to compile time, not to runtime. The code is still efficient that we generate.
Is it only slightly longer than a straightforward parsing?
Well, I didn't do. I mean, we don't have any other reference implementations, so I couldn't really tell you, how we compare in terms of benchmark. Yes, it is slower, but by how much I cannot tell you.
And one more question: the game you showed, the full game. So I'm assuming it didn't like cross-compile out of the box. How much work was needed to change the original game that they wrote for Android to actually pass the cross-compiler and work properly?
Well, so your question was how much work did we have to put in to cross-compile this Legions game?
Yes.
Or how much changes were required in the Legions game itself? Mm-hmm. Well, first of all, we had to put in quite a bit of effort to push XML to the point that it could cross-compile Legions.
Not counting the work on the cross-compiler itself.
But otherwise, the guys in Australia had not to make any changes to their application. That is
just the exit, like.
We just got
the exit button. Get rid of that. I mean, it was.
Well, of course, yeah. Well, when I saw that, I told them, okay, guys, we cannot cross-compile an exit button. Apple won't allow that. Mm-hmm. So we introduced certain API. We told them about it, but to my recollection, that was really the only thing that they had to change to make it work under XMLVM. Everything else they were using, from Sound API to activity lifecycle to all the layout managers, we took exactly as is without requiring any kind of changes on their side.
They didn't need to tweak it, like.
No, they did not have to tweak it. No.
Very nice.
So, what type of affordances do you have for debugging support?
Yeah, debugging support is a good thing, because the code that we generate, of course, looks ugly, right? I mean, if I can just go back here to Xcode, and I can just simply click on one of the cross-compiled classes. If you look at this here, that looks ugly, right? So our philosophy is that Objective-C is kind of like the assembly language of smartphone development, right? I mean, ideally, you don't really want to deal with it. But you are quite right, when it comes to debugging, that is a bit of a problem, because you cannot really correlate that back to the original Java source code. Mm-hmm. Now, if you have a working Android application and it crashes on the iPhone, then the solution is simple. There's a bug in XMLVM. So, I would suggest then just post a bug report on XMLVM and we will fix it. Now, the debugging happens under Android, right? And Android gives you all the powerful debugging tools. Right. So if the iPhone version then behaves differently or crashes even, that just indicates a bug in our tool chain. But basically, we take care of that, and you're shielded from that. So the good news is the debugging, again, we leverage the Android SDK.
The other question I had is, how do you deal with, how do you let the developer know when they're using a feature that's not really supported on iPhone? So for example, on Android, like there's a text-to-speech library that you can call from the APIs, which my understanding is that API isn't quite available yet on iPhone.
Well, you would notice during cross-compilation because there would be linking errors. You would try to link against something that's not present.
Okay.
So we don't have like an explicit list, API list, where you can look up and see which API we have covered. We should do that, I do agree. But at this point, if something is missing, if something we do not support yet, you would find out when you link, because then you have unresolved externals.
Okay, cool, thanks.
You mentioned support for the Palm Pre, the Android, and the iPhone. Is there any support for the BlackBerry?
Well, of course, we get a lot of requests. There's requests for Windows Mobile. There's requests for BlackBerry. At this point, XMLVM does not support these as backends. But I think we are in pretty good shape of very quickly targeting also these platforms. So the way we go about it is, like if we have a client who is interested in a certain feature, then we certainly put that high on the to-do list. But at this point, our main focus is the iPhone. Second focus is Palm Pre, and beyond that, we just let customers decide on what they want.
Android has a SQLite database, I believe. Does this cross-compiling also support that?
Okay, the question is SQLite. We don't have an API wrapper for that at the moment. But to my knowledge, the iPhone also has a SQL-like database that you can also access. So it would be possible, yes. Again, the thing is, remember that we don't have to re-implement features, right? I mean, when you talk about Compass, when you talk about accelerometer, when you talk about different features, usually all these devices have this capability. So also a SQL-like database is present on all these devices. It's just creating these wrappers. So actually making this mapping is not as complicated as it may sound. So we can very quickly, if there's a demand for a certain feature, we can fill this gap if it's not present at the moment in XMLVM.
Android also has the OS itself, I think the framework, or I guess it provides ways to communicate between applications, like you could register with the phone to be a media player and things like that. That's not possible.
Yeah, well, okay, of course, if Android has this notion of activities, and you can also call an activity from another application. So for example, if you want to select one of your contacts, you can call a sub-activity from another application. Now, the way we plan to address that, and we haven't done it for contacts, but we have done it actually for web views. We have implemented an activity that will be linked to your application, so that it looks like on the iPhone you're switching over to another application, but in fact you're still within the same application that you have launched. So I think in many cases we can deal with that. So we do not do multitasking, which is not allowed on the iPhone anyways. But we plan to implement special purpose activities that kind of mimic what you have on the Android.
So you'll kind of launch the dialer you link with the dialer. And when I click on a button on my app, it'll actually show the dialer window that you linked with in my app.
And then the special purpose activity then will mimic whatever you see on the Android, but it will also, of course, make use of iPhone specific features. Any other questions? Well, if not, then again, thank you for coming today, and thanks for listening.